Okay, we're back. Let's continue. We don't have a lot of time. Brought some hinges, since we mentioned hinges. But you might want to look at them and get an estimate of how much difference there is in size. You'll notice also the hinges don't come out. You might want to try and figure out why that is, so I'll pass these around. Actually, let's start one back here because we'll kind of pass it back rather than across. And I'll show you something I made in graduate school. This is supposed to be what's called a popper. It's something for graduate students to do, I guess, in a class. And the idea was we were supposed to make the shaft a very precise diameter on the lathe, and the hole a very precise diameter, so that they fit together with a very fine fit. And the idea was you should be able to pull them apart, and they would pop because of air pressure. And then it doesn't work. And I was very careful when I made this. I was using a micrometer. I measured that diameter very carefully, made it very precise, made a decent surface finish on it, and I couldn't get the darn thing to pop. And my professor came over and he looked at it, he measured it carefully, he measured the hole, he measured the shaft, and he put it together, and it wouldn't pop. And then we had the teaching assistant come over and say, hey, what's wrong with this thing? And the teaching assistant said, it's hollow. You've got a hole all the way through. Of course you can't hold air pressure. Put your hand over the back, and it pops just fine. Okay. So when I was so focused on the fine detail of making these the right size, I couldn't notice that I'd picked up a part that already had a hole drilled in the back of it. So if you want to pop that, you're welcome to as you pass it around. So the fit there is fine enough that it actually holds air. This is similar to a piston. Now, a piston usually has actually more clearance than that has. A piston in the cylinder has more clearance. It's the rings that actually rub against the side walls and create the seal. To demonstrate different classes of fit, I took a ball bearing apart. Anybody ever took a ball bearing and took it apart? This is the outer race, the inner race. It's actually not all that easy. You have to take the cage off, get all the balls to one side, and then get the inner race out. So I succeeded. I don't really need the outer race. I just brought it with me to show you. And then I very carefully turned down 3 different sizes of shafts. Okay, I've got marker on the bottom, A, B, and C. Now, when you put the inner race, the bearings are very precise, and so this inner diameter has been cut to a very precise amount. So when you put the two together, you can actually feel the fit and get an idea of how close they are. Okay, some will feel a little more sloppy than others. Okay, so you can actually put it together and feel the fit between. Well, don't force them. If you turn it as you're putting it on, if it's a real tight fit, you may have to turn it to get it on. They're all clearance fits, and you can feel the fit. I'm going to pass these around. I want you guys to, as I'm talking, put them together. Just decide which one you think is the tightest fit, next tightest, and then loosest. So look on the bottom and write A, B, C on your paper to decide in order which one is we'll take it from tightest to loosest, okay? Try to not wipe off the bottom. Those are just dry erase markers. So I need to put a permanent marker on them someday. All right, anything else? I don't think so. I think that's all we needed. All right. Remember I talked about pressing 2 pieces of material together, a male and female part, one where the male part was actually larger than the female part. It would be an interference fit. I've experienced this. I will tell you part of my Saab story, my SAAB story. It's one of the engines that I rebuilt. I don't have the car anymore, but my former spouse and I were trying to go somewhere, and the engine messed up on us. And so we had to be towed back. It was a really disappointing experience. That was pretty frustrating, but I knew I could rebuild the engine, so I did. It's the first front-wheel drive car I had rebuilt. I found out you had to take the engine out the bottom. So you jack up the car, you support it. It turns out you have to take the wheels off the front, okay? And there's a whole sub-assembly that you can drop. You'll have the engine and transmission all together. Take the engine off, rebuild it, put it back together, and hopefully it works. Well, so I did all this work, went through it, had the head rebuilt. What had happened in the darn thing is that it was a 4-cylinder engine, and it had what's called balance shafts. Balance shafts basically have counter-rotating weights that are supposed to cancel out the shaking forces generated by the pistons moving up and down. Theoretically, you cannot balance a 4-cylinder engine perfectly. Okay, and so you have to add something in. It's common for 4-cylinder engines to have and include balance shafts so that your engine doesn't shake too much. Well, come to find out, the shaking forces generated by the piston are actually not all that large. And so a common failure was the one that I experienced, where the balance shafts locked up and then basically threw the engine out of time, and now you got to rebuild an engine at a very high price. And so the balance shafts really weren't worth it on this car. It was a Saab 9-3. So I just took them out. And in taking them out, because they were actually driven by a chain, but the chain was about the size of a bicycle chain. It was even smaller. It was tiny. I thought, how the heck do you put something like this in a car's engine? It doesn't make any sense. So I took the balance shafts out. The bearings that the balance shafts were supposed to ride in were about so big around, and they were supposed to be 1 inch long. When I took them out, that section of the engine had been starved for oil for so long, they had been rubbed to literally 3 inches long. Okay, so think of a tube that should be 1 inch long, it's 3 inches long, where the metal has been smeared over time, essentially. And so, of course, those balance shafts were not going back in. I found some tubing that I basically glued into place with special glue, blocking the oil cavity, because there's nothing there anymore, and I needed oil pressure in the engine. And it worked fine. Well, long story short, I got the whole car back together, the moment of truth, turned the key over, the car fired up, I was so happy. Fired up, ran, sounded beautiful. I was like, okay, thank goodness, I'm so glad. So I put the front wheels back on, and that's where I made a mistake. Turns out that with front wheels on a car like this, there's drive shafts that go out to them, right? Okay. Well, the bearings that ride on the outside of, really it's a CV joint, is what it is. The bearings that ride on the outside to support the wheel have to be pressed into a housing. Well, the problem is that the bearings are actually a split bearing. The outer race is split. Okay, and so if you don't apply significant axial clamping force on it, the two outer halves of the outer race will separate, and you'll destroy the front bearings pretty quickly. Well, that's what I did. I forgot to tighten down the nut because I was so excited that the engine ran. I wanted to take it for a drive, so I just put the wheels on and went. And I forgot. And of course, about a week later, every time you turn the corner, you hear this grinding noise that sounded horrible. I completely destroyed the bearings on the front wheels of that car. So I took it basically was an integrated strut and housing assembly the bearings were pressed into. So I took it to where I worked at the time, which was Amatrol, because they had a hydraulic press. I was going to press the bearings out. Well, it's a good thing that nobody was there when I did it, because when the bearings finally came out of this darn thing, it sounded like a shotgun going on. It was so loud. Apparently, the way they did this is the bearings, now remember it's the outer race that was pressed into this housing. Apparently what they did is they heated up the housing and cooled down the bearing to drop them together with a force fit. So anyway, that's a segue into what we're about to talk about here. When you have a force fit, there can be significant forces between the male and female part, because the male part's bigger than the female part. And so the amount of pressure in that zone is something of interest. How do you calculate that pressure? Well, here's an equation to do it for us. Okay? It's based on some things you learned in strength of materials, but we don't really care about the details, we just care about the final result. So you need the elastic modulus of the material. You need some parameters, A, B, and C. Now we need to be careful here. Here's something that students always confuse. You ready for this? Students always get confused because they see a hole in the middle of this part, this light gray part. The part, what we're interested in is this interface, not this interface. This is just a hole. So this light gray part is really the shaft, and it's the outside dimension that we're interested in there, okay? Now we're interested in radii, not diameters. These equations, I'm going to show you more than this, all use A, B, and C as radii, not diameters. If you use the diameter, you'll be off by a factor of 2. Okay, if I remember right. Maybe, I don't think it cancels. No, it might in this case. No, it doesn't, because see, you got B right there. So if radius versus diameter won't matter here, but it will matter here. So be careful, always use radius. The other thing that students get confused about, if this shaft, instead of being a bushing with a hole in it, if this shaft were solid, what would the dimension A become? Notice that A is the size of the hole. If the shaft's solid, what happens to A? You get 0. So anywhere you see A in the equation, you just plug in 0. But be careful, you might want to make some notes. What page is this? It's 497. There's a whole section, procedure for computing stresses and force fits. if I were you, I would highlight some things. Maybe write radius right next to the figure, okay? Because A, B, and C are all radii. Also maybe you write A equals 0 when it's a solid shaft. I don't know, it's up to you. But those are two areas where students frequently make mistakes with this particular subject. Now the equation that you see here, you'll notice it's equation 13.2. This equation is only good in one case. It's only good in the case where both the parts are the same material, or at least have the same elastic modulus and the same Poisson's ratio. That's the only time that you can use this equation. All right? If these are different materials, say you have an aluminum part with a steel part inside of it, if that's the case, both aluminum and steel, then you have different elastic moduli and different Poisson's ratios. In that case, you can't use this equation. In that case, you have to use something a little bit more complicated. Okay? This is equation 13.3. This is just the equation when there are two different materials. Notice you'll have an elastic modulus of the outer member and an elastic modulus of the inner member. And you'll notice that the inner member only references A and B because those are dimensions of the inner member. The outer member references dimensions C and D because those are associated with the outer member. Now, I haven't talked about this delta yet. What the heck is that delta? The delta is the interference between the two. Okay, so let's say that the shaft is made to be it comes out and the shaft is 1.001 inches in diameter and the hole is 1 inch in diameter. How much interference is there? There's 1,000, right? 0.001, exactly. That's the interference, and that's what would go right there. Basically, it's the amount of overlap. Now, does it matter? The question then becomes, well, what is B? Is B a half inch? Or is B 0.50005? Did I get the right number? 0.5005. In other words, a half 1,000. It doesn't matter. It's not that sensitive. You can just put in the nominal size there, the nominal radius, and it'll work just fine. Where it does matter is in the interference. Okay? So there's the equation. If you want to, I will let you use a laptop on the exam. You might want to make a spreadsheet with these equations so you don't have to type them in or make a mistake on your calculator. Just do it now. Yeah.
Yeah, so he and I were just looking at the book, and I noticed that, like, right beside in the book, there's an equation for thermal expansion.
Yeah,
and
equation 13.1.
Yeah, and it uses delta as well. Will this equation ever come in contact at all with the force fit?
You're saying, what about all these deltas running around?
Yeah, that's what we're worried about.
Well, it could. Think about it this way. I could give you a problem where I say, okay, I've got a shaft that measures 1.001 inches in diameter and a hole that's 1 inch in diameter, 1,000th of interference, okay? Tell me what I need to do temperature-wise to make it so that I can just put those two things together without any force. In other words, what temperature do I have to take the shaft down to so that it'll be 1 inch in diameter? Then you know what the delta is in equation 13.1, right? You know how much the size needs to change in this equation. It needs to change by 1,000th of an inch, right? So then you could calculate the required temperature change of the part, right? And then I could say, okay, now I've done that and I've put these two parts together. Now calculate the pressure once they come to thermal equilibrium, right? So now they're at the same temperature. So they're back to room temperature. Well, now what's the interference? 0. It's 1,000th of an inch. It's not 0, it's 1,000th of an inch because that part, that male part originally measured 1.001 inches and the female part measured 1 inch.
Oh,
right?
I was thinking it was like part B to where you had gotten the definition down to 0.
Right, I understand. Right. So, but once they come to thermal equilibrium, now that 1,000th of interference is still a real thing that's being resisted, right? It's not, I mean, the shaft will not be 1.001 inches. It's being constrained by the outer material, right? But there's significant pressure between the two, and this is how you calculate the force. Why would you care about the force between the two? Why would it matter? Maybe too much, right? Maybe too much force. I mean, you can really cool things down and heat the opposite part up and put them together, but it's possible they'll crack. It's possible that the stress will be so high that they would fail. And so getting the pressure will help you determine the stress of the material. So that's why we're interested in it. Another reason you may be interested in it is because that pressure is effectively a force preventing motion. It's like a normal force, and you can calculate the friction from that, and then tell how much force it takes to pull it out. Because interference fits are one way of assembling parts together. Let's see. If you're interested in the diameter of the shaft and the hull after they've been put together, there are two more equations, equations 13.6 and 13.7, that you may be interested in for calculating that, but usually that's not all that interesting. So most of the time we won't use equation 13.6 and 7, but of course you could put them in the spreadsheet if you wanted to. You've got everything else you need. What's a little bit more interesting is the compressive and tensile stresses, equations 13.4 and 13.5, which allow you to calculate the tensile and compressive forces in the members. Okay? And so I've got those included on the slides. But notice you need the pressure at the interface before you can calculate the stresses. Okay? Questions, comments so far?
So that's the one you would use for different materials?
This is the equation we use when we have two different materials, but you could still use these two equations even if you have the same materials. Because these are just talking about stress once you have the mating pressure between the two materials. So there's the deflection equations that I said we probably will not use. All right, so that's everything from chapter 13. Let me see if I have any example problems for you. I don't think I do. This chapter is actually pretty straightforward. In fact, I don't think I even have any problems. Yeah, I don't. Yeah, there's not that many. I don't even have any homework assigned problems for this, but I may throw it on an exam. Where I really want you to use this, I'm trying to give you a lot of different tools because in the project I will require that you have 3 sized machine elements. Okay? Usually students will size a fastener because it's pretty straightforward. They'll size, some will do like a weld, some people will size a key. Here's another one you can size. You can figure out the pressure in an interference fit if you wanted to. And I think that this may be really relevant, which is why I included in the slides this semester, because we're going to be designing machines that are a little bit smaller than we have in the past. And so an interference fit is sometimes a really clever way to put some parts together, hold them without an extra fastener, which can save space. Do you have a question?
Well, actually I just thought of one. So
Yeah.
we were discussing before class, I know that we're, kind of set on, the plastic versus plastics, but like,
Yeah.
do you feel like in, maybe in future classes, not even necessarily this one, but like, you could ever go like the battle bot kind of route?
Oh yeah, that'd be fun. Yeah, we could probably do that in mechatronics. In fact, that's maybe a good idea for mechatronics. We've been talking to mechatronics about what project we're going to have and haven't really decided yet. So thanks for the idea. That would be popular, wouldn't it?
Yeah.
That's a good idea.
You wouldn't even have to build that many, like,
Yeah.
you just build 2 and then just.
Yeah, it's a good idea. The only reason I wouldn't want it in this class is because the control side is so important, right? I mean, it's not just a machine that's mechanical, but I love the idea. Thank you. That's good.
Let's make demo cars.
Demolition derby cars? Do it out here in the parking lot, why not?
Yeah.
When it starts to snow.
Run them next year at the next demolition derby, at a fair or something. See what happens.
There are actually things I'd like to do out in the parking lot. There's a lot of things. One of the ideas I've had in the past, I don't know if you guys are familiar with projection mapping, but it's used in augmented reality quite a bit. And basically you just project an image onto a surface, like it becomes a big theater screen is what it's like. But you can do interesting things. It's especially used for haunted houses and things like that, where it makes it look like the house comes alive for a moment. And you can really do some mind-bending things, especially when everything else is dark and all the eye has for reference is the light bouncing back off of the building. During daytime it's not very effective, but at night you can really do some interesting effects. So there's a lot of things I'd like to do. The battle bots though sounds doable. I like that a lot. Another thing, of course, in the past we've designed. Well, let's continue talking about the project. In the past, we've done several things. We've designed, I'm trying to think of what all we've done. We've designed hovercrafts and not built them, and we've designed hovercrafts and built them. We've done both. The ones that were designed and actually built didn't work very well. The ones that were designed, we don't know if they work. Another problem that I've had, I've got that 72-inch mower I told you guys about, I think. The deck's on front, and there's a lever, hydraulic lever basically for raising and lowering the deck. Okay? It's an older mower, but I like it. It works fine. And the interesting thing about it is that the engine is in the back, and there's a hydraulic pump basically that it's coupled to, but there's a shaft that runs from the engine forward and then goes down via two V-belts to drive a shaft that goes, it's actually mounted through the differential, which is in the front, the differential case, and then has essentially a power takeoff that drives the deck. Well, the neat thing about this mower is you can pull the deck right off. In fact, I'll show you what it looks like. Ford New Holland CM272, I think is what it is. If you look it up, you'll find people trying to sell these. But basically, this is what it looks like, and you can see here how the deck can be raised. And you can't see it real well here, but these arms go into the hydraulics basically and can be removed, so the whole deck can slide off. And there's actually a shaft that comes out. The front wheels are driven. There's a differential there. It's a big solid cast iron piece. But there's a PTO that comes out and drives through a shaft to drive a gearbox and then turn the blades. You can see it a little bit better here. This is the gearbox here. There's a shaft coming out right here. Anyway, one of the devices that was available for this, you could actually take the deck off and put a snowblower on it instead, which is kind of cool. Or you could get a smaller deck, or that was the biggest size deck, it was a 72-inch. But it was a neat thing because it was a commercial mower, but you could get it for your home too if you really wanted to, if you had a big area that you needed to cut. And have a tool that had multiple uses, kind of like having a small tractor. Well, I got to thinking about it, and I thought, you know, it'd be cool if I could take the deck off and have a wood chipper instead. Couple up a wood chipper to it and use it. You know, that'd be kind of nice. Because I've got a lot of trees, and I love my trees. I've got ash trees. I don't know if you guys have ash trees, but ash trees are being destroyed around here by the ash borer beetle. Well, it turns out you can actually get them treated. You can get your trees treated. There's like a 99.9% chance they'll recover and live. And my house is actually framed by all these big, beautiful trees that would take, you know, longer than my lifetime to grow. I wanted to save them, so I actually called a local company that came out, and it cost a couple of grand, but it was worth it. Actually, it was less than $2,000. It was like $1,700 or so to have about 15, 20 trees, something like that, treated. And what they do, it's kind of neat. They drill into the bottom of it and then have a pressurized container of, not medicine, but whatever the chemical is, and they actually inject it, and the tree actually sucks up the medicine, distributes it throughout the entire canopy, and the bugs start dying. So I've had that treated, but why did I go off into that tangent? Oh, so I've got all these trees, and I end up with a ton of sticks in my yard. And I've got to pick them up, and I thought, you know, it'd be nice to just chop them all up. So at one point, I was thinking about designing a wood chipper, so I had the class actually design one just because it was an interesting project. We didn't build it, and I don't know if I'd wanted to have built the designs that I saw, but we did it nominally. I am open to suggestions. Why don't we take a few minutes? We've got 30 minutes in the class. I know you guys are probably tired of the material going through the subject. Why don't we take a few minutes and brainstorm? What kind of things would you like to do? I think the precious plastics is interesting. What do you think? We've had demolition derby cars and fighting robots so far, right? We got to start. What else?
I think the wood chipper.
You like the wood chipper? Okay.
Yeah.
What about a wood splitter?
A wood splitter would be cool. I like that. Yeah.
Like a faster wood splitter. Yeah.
Well, have you guys ever seen the videos of
The inertia
ridiculous?
ones, I've seen that.
Yeah, the inertia ones. Yeah. We could do something like that.
I've seen one made out of a square baler, but it was a little dangerous.
Made out of what?
A square baler. It's
Square pegger?
Square baler on a hay baler.
Square baler. Okay.
They took everything hay baler part out of it.
Yeah.
Except for the plunger, and put a wedge on it.
Put a wedge on it. Okay. So basically, the hay baler just punches the hay, I guess, and presses it down. Okay. All right. What else?
I mean,
There are some pretty wild machines out there. Have you ever seen? Let's see if I can find it. Have you guys seen this machine? It's really neat. It goes down either side of a row of orange trees and basically shakes the canopy to make the oranges fall. So there's some wild and crazy machines out there you may not have thought of. Yes, sir.
Can you look at the bench rack?
Sure, what is it?
It's like.
I'm sorry, I didn't hear the words.
Bench rack.
VENTRACK?
Yeah, go to the website.
Is this it?
Yeah,
Okay.
the website has a video on it.
Should we watch this video, or is there one you recommend?
Is that what you want?
Yes.
No, not the project, obviously. I just wanted to see it.
Well, it looks like interesting. Oh, kind of interesting. We're talking about, looks like a front end loader versus a
Way off topic.
What's special about it?
You can have different attachments on it.
Different attachments? So it's smaller than a regular tractor, it looks like.
It's not.
It looks like it's got an engine on it, because I see, looks like a muffler on the side. So they're going to compare these two, I guess, and tell us if their product is better, based on how long it takes to move a pile of mulch.
You guys
What are you trying to show? We're gonna make some ramps at your house, right? We're trying to come up with ideas.
I know.
Well, guys, during brainstorming, no idea is a bad idea. Okay? So I don't mind looking at things to see what, it may generate some ideas. You actually reminded me of something we did in the past, and I'll show you here in a minute. It looks like the purpose of this is to not destroy your lawns and yet be able to move stuff.
This is far as tire tracks and whatnot.
Yeah, it looks like it's not a tractor tread, it's a tire tread. They're claiming their little machine can do it faster than the big machine.
There's a better video on YouTube. I was trying to show different attachments.
Okay, where's the? Okay.
Blake has an idea if you want to see it.
What's the idea? Tell me.
Very professional.
Like with a
Shopping cart, it's a go kart. It's a shopping cart. See, I was thinking that too.
Okay, guys, let's watch this and see what this is. I'm curious.
Come on, guys, Jake wants to show us the video.
It's actually shopping.
Ventrac is a unique compact tractor that offers significant advantages no other equipment can match. It's the type of equipment that solves problems. Right away, you can tell that a Ventrac isn't built like any other piece of equipment. The articulated and oscillating design both protects the terrain and makes the tractor more capable and easier to use. And full-time hydrostatic all-wheel drive ensures that the capability of a Ventrac is unparalleled. This gives you stability, comfort, and control that you don't get with a typical straight-frame tractor or mower. Purchasing high-quality equipment for each and every task can often be difficult, expensive, and sometimes even impossible. Ventrac's most obvious advantage addresses these concerns.
You guys notice that?
Yeah.
Well, what are those?
Double block bearing.
Double block bearings. I didn't know they do use it.
Its most obvious advantage addresses these concerns by having over 30 different attachments for use in all 4 seasons with one tractor in support of one single pedal. It's also important to note that each one of those attachments can be connected in a matter of minutes with one operator and no tools.
That's what I need right there. Exactly what I need. That was one of the attachments I was going to suggest we could design for my mower. Because I need one.
One thing Ventrac is known for in particular is our mowing capabilities. From finish mowing to field grass mowing, slope mowing, even golf course mowing. If you're mowing a steep slope, you want the capability and peace of mind of a Ventrac. With the capability of mowing slopes up to 30 degrees in any direction, Ventrac is simply a safer, more productive solution. For sidewalk snow removal, there's no machine that's even in the same league as a Ventrac. With ultimate maneuverability, highest quality attachments, and heated cabs, using a Ventrac for snow is easy and stress-free. When you buy a Ventrac, you don't make any compromises. When we build them, neither do we. Ventrac tractors are made in America, focused on quality materials and legendary service. According to our customers, a Ventrac is many things. They tell us it's a machine they wish they would have purchased sooner. They also tell us it's a machine they plan to purchase more of. Most of them tell us it's the safest machine they own. But it can all be summed up by what the majority say: it's the best equipment purchase they've ever made. That's a Ventrac.
I wonder how much each of those attachments cost. Certainly interesting.
How much would all that cost?
Yeah, that's certainly an interesting device. I mean, I just paid the guy to come and grind down a bunch of stumps out there, because I had to cut down a bunch of trees a couple summers ago.
$5 rent, especially equipment over something that can do multiple stuff like that.
Black powder works better.
Black powder. Here's something that we did. We didn't actually build these, but have you guys seen this? Another very interesting mechanical system. Tracks. Yeah. I would love to have these. You know what I'd like to do? I'd like to build some of these that work, put them on my car, or at least that look like it. Come out here, put my car up on them, right beside Professor Deuce G.
You do all the fabrication, all right?
The Track and Go is another project we've run in the past. Trying to think of anything else we've done. We've done a lot of things. We've talked, of course, for a while.
Okay, if we were doing go-karts, I wanted to make a shopping go-kart.
A what?
A shopping go-kart.
A shopping go-kart?
Yeah, the frame is like a shopping cart.
Okay.
You put a little platform on the back and put the engine on it.
Gotcha.
Get a few shopping carts.
Because you can have setting on the ground. Like,
Okay.
Oh, okay.
you can
Like
cut
separate
it,
around,
yeah.
yeah.
There's
You just gotta go
pictures-
steal a bunch of
there's
go-karts
pictures
from
on
Walmart.
here.
Or shopping side like almost.
I'm sure there are. So like this?
Yeah.
Yeah. This is something that's a little more.
Wait,
These look like they have a frame, whereas this one actually is the car itself.
Yeah.
You might put the shopping cart on a frame, but I think it would look.
Yeah, sure.
We go to all these and get them for $1.25.
No, just 25 cents. That's all.
No, we're getting $5.
Oh, 5 of them, gotcha, okay.
You just take them back, we're done.
Engine and all, with the little quarter stuff. Yeah, all these cars. What else? We're brainstorming, this is fun. What else would you guys like to build? I'll tell you one of my crazy ideas if you don't have any. When I bought my house, I shouldn't have, number one. But when I bought it, there's a basement. And the thing is that the house used to have an outdoor room on the first floor. And so in the basement, there's actually a walled off 8-inch thick concrete wall that is 14 foot by 20 foot. And so I can't use that space because it's full of dirt in the basement. And it's a big pain because you have to walk all the way around in the basement. It takes up a lot of the basement's usable space. Well, eventually I want to get that dirt out, and there's many ways to do that. Some of it involves potentially designing a machine, okay? The first problem is I've got to cut into the concrete, cut through 8-inch thick walls. And it is load bearing, okay? But if I'm only cutting a 6-foot wide doorway out of a 20-foot wide wall, right, and I've got supports for the floor, and then I put in a beam, the concrete can take the stress. I'm not worried about the structural integrity of the house. I know how to deal with that. But it takes a long time to cut through that concrete. I've already done it once. I don't know if you guys have seen this saw. Let me show you. They're getting harder to find. Dual blade. I'm trying to think who made it. Husqvarna. There we go. Yeah, hang on just a second. Hold that thought. Let me show you this quickly. Yeah, it looks about like this. It's kind of neat the way it works. And mine's electric. Mine looks like this actually. That's exactly the one I've got. And I didn't pay that much for it. I bought it used. But basically it has 2 saw blades side by side, and you drive the saw blades into the concrete. They're diamond saw blades, and you run it up and down the concrete, and you basically make a cut that's about that deep and that wide, okay? And then you just break off the piece in the middle, and then you can plunge deeper, okay? And you can cut through a very thick wall this way over and over. It takes a while. But anyway, I've used it already, and it takes a while, so I've thought of, is there some way of making a frame that you put this saw on where I just get it started and walk away, and it applies force and slowly makes the cut. You know? So it's another machine I'd like to build. What were you going to
You
say?
do like some sort of like tree debarker.
Tree
It's
debarker?
got like a barrel grinder on it, or
Yeah.
drum grinder, and it pulls the bark off.
I think that's really interesting.
Like they got sawmills all the time. I seen one the other day, and I thought it was pretty cool.
Well, all those trees I cut down, I thought it was a shame. I'd like to actually build a gazebo in the middle of my pond. And I thought, you know, I've got all these long trees. It's kind of a shame to have to cut them up for firewood. It'd be nice to debark them, turn them down, and use them as posts.
I cut down some trees around my shop the other day, and I had to shave. I'm putting a gate out front,
Yeah.
and I shaved 2 posts down with a hatchet, and I had a debarker.
Yeah.
It would have been nice.
Well, I found out something. Some of the trees that I cut down, I left laying in my pond for about a year. When I pull them out, getting the bark off is really easy. It falls off. Yeah.
So like, I don't know, I was just kind of thinking of an idea, just for like our class on the side, an idea, is there any way that you can maybe like, make something on Blackboard that like, you know,
Yeah,
we've got a long
make a list.
weekend, and we can kind of submit maybe like one idea apiece, and then we can kind of vote on it.
I like that.
I
Let's
get
do
a
that.
little drunk this weekend and start thinking of stuff.
Wait a second, drunken machinery does not sound like a good idea.
The ideas can be good, just not deciding while you're drunk.
Hold my beer.
Yeah, what I'll do is I'll start a discussion on Blackboard. Give us an idea, I like that. In the time we have left, why don't we get back into some of the course material? And I'll post on wild and crazy ideas too, okay? If you can include, I'll try to see if we can include some pictures. So that way you can give us some context. All right, let's see. We have basically finished off tolerances and fits. Let's go ahead and turn on shaft design. Shaft design is the last topic before the first exam. Shaft design is the hardest topic we will have encountered so far. We'll probably make it through the slides, but the devil's in the details. So it won't be until we get to a example problem that you'll see that these problems take a while. And even when I work one in class, it'll take at least a whole class period, sometimes 1.5 class periods to work a shaft design problem. All right. Our demotivational poster. Teamwork, ensuring that your hard work can always be ruined by someone else's incompetence. All right, so in talking about shaft design, this is chapter 12. Oh, by the way, one thing, in the brainstorming, when you see someone else's idea posted, you're not allowed to critique it. No critiquing. Notice I haven't critiqued anybody's idea. That's because we want to generate as many ideas as possible, and then we'll critique the heck out of them, okay? So we will critique. We're not going to do something wild and crazy, but we'll save that for later. All right, so in shaft design, how are we going to do it? Well, we're going to determine rotational speed, so how fast does a shaft have to run? What are the torque loads and where are they at? Consider where we want to put the various machine elements, pulleys, gears, bearings, etc. Okay, and then determine the shaft and locate the components. Okay, so when you're designing a shaft, we're not talking about a shaft that's a simple half-inch shaft that's 1 foot long and you're just mounting machine elements along it. We're talking about serious shafts. In fact, think I might have a shaft laying over here, so here it is. I'll pass it around. This is the kind of shaft I'm talking about, okay? Something that is engineered. It's not just a straight single side or size. You'll notice this one has been broken off the end. There's a failure on the end, if I remember right. I think it's a fatigue failure. But there are steps in the shaft. There are keyways, there are threads, there are grooves, there are all sorts of things. And in my opinion, this shaft designer wasn't all that great. They must have had some reason for doing the things they did, but I'm not terribly impressed. There's another type of key here. This is a Woodruff key, whereas this side is a straight, this is called a sled runner key, and I'll pass this around in a minute. You'll notice that there are different surface finishes along the length. Run your fingernail along it and you'll feel the difference. There are steps in the shaft. There's actually a pin right here. So look at it and see what you like and what you don't like about it. I'll start it out in the back because I've started everything else out in the front. I want you guys to look at it and see what you think of it. But this is the kind of shaft we're talking about, where there's going to be multiple features along the length of the shaft, and we have to specify all the details about it. So we'll have to calculate all the loads that are acting on the shaft. We'll end up drawing shear moment diagrams. Do you remember in 211 when we drew shear moment? Well, they're back. And this time, guess what? The shaft can be loaded in two different planes, right? You could have forces acting this way and this way. And so we'll end up with two shear moment diagrams for each shaft. Each shaft will be very much like a beam. And so 211's back. We'll select a material. This will tell us how much stress we can apply to the shaft. And then finally calculate minimum dimensions, minimum diameters basically along the length of the shaft. And then finally specify the final dimensions along the shaft. See, the minimum dimension is not, it's not like that's the right answer and the shaft has to be that size. You can upsize it a little bit. If you change the size and increase it just a little bit, well, you've got a slightly stronger shaft, right? So there's nothing wrong with it. All right. What factors might affect shaft design? Well, there's a couple things. There's a few principles you need to watch out for. You don't want excessive deflection in a shaft. Okay? Tension in belts actually bend shafts. How is that possible? Are you saying that, I mean, you've all seen a shaft that's supported by a bearing, and then on the outside is a V-belt pulley, right? You got a V-belt on it. Of course, you put that pulley outside of bearings. You don't straddle it with bearings because you need the ability to get the belt on and off, right? So they're cantilever shafts. And the belt actually has to have significant tension in it so it doesn't slip on the pulley. Well, that means that belt is applying a load to the shaft, right? Do you think we're going to tension down a rubber belt to the point where the shaft, the steel shaft, will literally bend over and break? No, that's not going to happen. How would an over-tensioned belt make a shaft fail when the belt is just rubber? By fatigue. Think about it. If this is the shaft and the general direction of the belt is downward, as the shaft rotates, the direction of the load relative to the shaft is changing constantly. So basically, the belt is doing this to the shaft, applying a fully reversed load to it and causing fatigue in the shaft. Okay? So over-tensioned belts will cause bending in the shaft and ultimately fatigue failure. Okay? Now, the forces from the belt can create a slight angular deflection, but unless the shaft is way under-designed and undersized, the angular deflection is usually not significant. However, another concern is whipping, or the natural frequency. The natural frequency of the shaft is something that's very important. Now, there's a couple ways of, do you guys know what I mean by the natural frequency? Well, what happens is when you run the shaft at that speed, it starts vibrating, the oscillations grow farther and farther. Okay, and you can end up with some serious problems that will cause damage in the machine and failure of the shaft. There's a couple different strategies for dealing with natural frequencies and resonant frequencies is what they're also called. One way is to increase the shaft stiffness. Now, a shaft is usually made out of steel. We usually don't make shafts out of aluminum because shafts see a lot of loading cycles typically in their lifetime. And so we need to use some material that can be designed to last for an infinite life. And aluminum never has an infinite life. Okay? Steel is the only thing that you can, well, it's not the only thing, but between steel and aluminum, steel can be designed to have infinite life. Well, if you need to make the steel shaft stiffer, changing the material is not going to do it, right? Changing the alloy won't make any difference because the material properties are about the same in terms of the elastic modulus. The elastic modulus of steel is about 30 million, right? PSI. And you're not going to change that by going to a different alloy. It'll change slightly, but not much, not enough to do anything for you. So all you really have available to you to affect the stiffness of a shaft is its size, its diameter, basically. That's the only thing you can do. The thicker the diameter, the stiffer the shaft. Now, if the shaft is stiffer, its resonant frequency will go up. So let's say that you have an engine and you're concerned about the resonant frequency of a shaft in the engine, and the engine is going to run up to 10,000 RPM. Well, if the natural frequency of the shaft is 20,000 RPM, you never hit it and you're fine, right? And you have to be careful about harmonics, but we'll get into that later. Right now, we're just looking at general ideas. So another way is if you can't increase the size of the shaft, you might be able to decrease the size of the shaft and make it more flimsy, okay, less stiff, and actually lower the resonant frequency. And then in operation, just accelerate quickly through the critical speed, and you never really operate at the critical speed long enough for the amplitude to grow, okay, and cause problems. So anyway, that's something to watch for and something to know about and be concerned about. Common shaft sizes. If a shaft is less than 3 inches in diameter, you can actually get cold rolled steel shafting. And here's something you need to know too. Rod stock is different than shaft stock. Does anybody know what I just said? Have you ever experienced that? Maybe, maybe not. When I was an amateur, I had to design a shaft. It was a small shaft. I thought, heck, we'll use 1/2 inch rod. No, we won't. 1/2 inch rod, the tolerance on 1/2 inch rod is much wider than on shafting. In fact, on 1/2 inch rod, it could be oversized. Shafting, precision or accuracy shafting, is made and controlled to be a few thousandths undersized. Not only that, but, and you can get it, you can specify what you want. Not only that, but it's straighter than rod stock. So never try to use rod stock to make a shaft unless you're going to turn it down. Okay, if you turn it down from rod stock, then you can control the size of it wherever you want. So when you buy shafting that's under 3 inches and that you're just going to use it straight, if you make any cuts in it, especially a key, sometimes the shaft will have to be straightened somehow. Because when you remember, well, it was 211 when I showed you guys the video of the machinist that had a plate, he cut some out of it and made it warp. Well, shafting works the same way. There can be residual stresses, especially if you're looking at cold rolled steel, right? Because there's residual stresses. So if you want to cut a shaft material and you don't want to use, you may not want to use cold rolled steel, you may want to use something like hot rolled steel so that it doesn't deflect so badly when you take material out of it. Between 3 inches and 5 inches, you could use cold rolled, but these shafts would all turn, and a shaft larger than 5 inches is always turned. So you won't find shafting in those sizes that I know. Okay, so our calculations will be based on ductile materials. We're not going to assume that we'd ever make a shaft out of a brittle material. The reason is because brittle materials can crack under impact loading. Even crankshafts on cars, even though they're cast iron, they're made of a cast iron that's somewhat malleable. So we will use the maximum normal stress theory of failure, and I'll go into that later. You don't have to worry about it too much. It'll be built into the equations we're using. If you did make a brittle shaft, you'd need to use something else than the theory that's in this book. It wouldn't work. And we've already mentioned that the stiffness of the shaft is a function of geometry. So what we have to do is we have to specify diameters, radii, key sizes, shoulder sizes, etc., and even things like retaining groove locations to prevent axial motion in designing our shafts. So these are the things we will have to specify. One thing that's really important in dealing with shafts, and in several points in this class, is the power torque speed equation. Have you guys seen this before? Okay, where have you seen it? Fluid power? Okay. So you see it again. Now there's a page that's really handy. Most of the time you see this form of the equation because it's convenient to have the power in horsepower, the torque in inch-pounds, and the speed in RPM. But go to page 695. This is a page you may want to copy and stick in the front of your book, or you may want to put a tab here. It's because this number, 63025, is a conversion factor that actually has units that makes all these other units work. Okay? If you want something else, say you want the torque in foot-pounds instead, well then the conversion factor of 63025 is wrong. Instead you would want 5252. Do you see that as the first row in that table? Okay. So it's really handy to know all the different conversion factors. It's page 695. You might want to make a note of it, because that's a handy place to find conversion factors so you can use convenient units. Could you could you get power out of this in, I don't know, kilowatts? Not that number. Well, you'd have to figure out the conversion factor yourself. But there is a kilowatts conversion factor on page 695. Okay. How many more do we have? We have quite a few more. We took enough time. I think I'm going to insert a bookmark here and call it a day, because I don't want to skip over this part. This is really important. So even though it's about a minute early, I'm going to let you guys out. And I will see you guys. Let's see, this is a Tuesday, Thursday class, so the Monday off does not affect us. So I'll see you guys on Tuesday.